So let's go to infinite ladders, people. Now there is one circuit in HCV, and that somehow goes like, let me just get the exact one. So there is one circuit here that goes like this. You have got 1 ohm battery, you have got a 1 ohm resistor, then a 2 ohm resistor, then a 1 ohm resistor, then a 2 ohm resistor, then another 1 ohm resistor, another 2 ohm, and so on. The circuit keeps on going. So this is how the circuit goes, and on this side you have attached a cell. The cell is probably 6 volts or something, right? So they can ask you 2-3 things. They can ask you to simply find the equivalent resistance across the cell, and that's one question. Apart from asking that equivalent R, they can ask you to find out the current that the battery gives. That's just one step after that. So if you know the equivalent R, then the current that the battery gives is EMF by that equivalent R. Or maybe they may want you to find out the current in any one of these resistors. So that's after that also. So we will start with the first step. We will try to find the equivalent resistance of this circuit. Right. Now the idea behind this circuit is that it's infinite, and infinite minus 1 is also infinite. So what I do is I take 2 points here. Let me call these points A and B. So let me say that I have got a point here which is A, and then I have got a point here which is B, and I've got another point here C after the first branch, and I've got another point here D. And what we claim is this: if the equivalent resistance between A and B is R equivalent, if R equivalent is equal to the equivalent resistance between, or maybe I will just use R naught, right? It's easier to write. So if R naught is the equivalent resistance between A and B, then the equivalent resistance between C and D is also R naught. That's because what you have done is, out of those infinite branches, you have removed one branch, the first one, and how many branches are left? Again, infinite branches are left. So if the equivalent of those infinite branches was R naught between A and B, between C and D also it will be R naught. And how this circuit can then be simplified is, I will keep the first one, I will keep the second one, but in place of the remaining all resistors, I will keep just one R naught. And so the circuit will then look like 1 ohm, and you've got a 2 ohm here, and you've got a R naught here. And now you will be able to see that this R naught and this 2 ohm must be in parallel. So their equivalent will be, for parallel connection of 2 ohms and R naught, I will get equivalent R as 2 R naught by 2 plus R naught, and that will be in series with the 1 ohm resistor here. So therefore R naught is equal to 1 plus 2 R naught by 2 plus R naught. So what I've done is, I have first found the equivalent of these two guys, and the green encircled resistance is 2 R naught by 2 plus R naught, and then the equivalent of this guy, 2 R naught by 2 plus R naught and 1, because they will be in series, is 2 R naught by 2 plus R naught plus 1, but that also should be equal to R naught, because that is what the assumption was initially to start with, right? R naught is the resistance between AB as well as CD. And so I've got this equation, and the solution to this equation will give me the value of R naught. So we will be able to solve this equation. 2 R naught plus R naught square is equal to 2 plus 3 R naught, and you will get something like R naught square minus 3 R naught, R naught square minus R naught minus 2 is equal to 0, and you will get R0 minus 2 into R0 plus 1 is equal to 0. This means R0 is 2 or minus 1 ohm, and we can discard the value of minus 1 ohm. So then we know that the equivalent resistance of the circuit is 2 ohm. The next thing that they can ask you is to find out the current that the battery delivers. So I delivered by the battery. So now I delivered by the battery will be 6 volt by 2 ohm, and that's 3 amps. Okay, cool, not an issue with that. And let us now try to find the distribution of current. So let us copy this entire figure, paste it here somewhere, and see how the current will redistribute. So you will have a current of 3 amps starting from the 6 volt battery, and that is shown here in the battery branch. So 3 amps starts, and all that 3 amps will be flowing in the 1 ohm resistor here. So you will have 3 amp flowing in this resistor, and 3 amp will arrive at the first junction, where 3 amp has to split into 2 parts. But what it finds is that the resistance that is kept ahead of it, so all that green encircled resistance is 2 ohm, and the other branch also has got 2 ohm. So this 3 amp will break into 2 equal parts, and what will happen is there will be a 1.5 amps going in the 2 ohm branch here, down 1.5 amperes, and 1.5 amperes will be going ahead in this 1 ohm resistor, at least 1.5 amps. Now this 1.5 amp will arrive at the second junction, and it will find that on one side there is a 2 ohm branch, but on the other side also it will find that the brown encircled resistance is a 2 ohm branch. So again the current will break up into 2 parts, because all you have done is from those infinite infinite steps, you have removed 2 steps, and again you have got infinite steps. So even the brown encircled part will have a 2 ohm resistance, and once you have got this 2 ohm resistance, at the second junction here, 1.5 amps will break into 0.75 amps and 0.75 amps, and you can figure out the distribution of current in the similar manner everywhere. Three amps of current starts going out of the cell. So here is this green colored 3 amps. It goes into the 1 ohm resistor, fine. So 3 amps is here, and then it goes to junction 1, or let me say junction P or something. So this is a junction P, and at junction P it should split into 2 parts. So now the thing that you need to ask yourself is, the current that goes into the 2 ohm branch is anyways going to experience 2 ohms resistance, so that's fine. But the current that goes in the 1 ohm branch, is that current going to experience only 1 ohm resistance, or after going through the 1 ohm guy, will it experience more resistors elsewhere? So the answer is that it is going to experience this entire network of resistors that we have put here, right? So the current that splits at P will not just do based on whether it is 2 ahead or 1 ahead. It'll see whether it is this entire segment ahead of it or not, and that entire segment ahead of it, let me just erase it, can be thought to be a 2 ohm resistor, because that's the equivalent of this infinite ladder, right? So now the current at P knows that it has to split into 2 equal parts, because the resistors are equal. So it splits into 1.5 and 1.5. Right, now this 1.5 amp goes ahead, and this 1.5 amps you will see will reach the next junction. Let's say the next junction is Q, here somewhere. So the next junction is Q, and 1.5 amps go there, and again at Q this 1.5 amp has a choice how much to go in the rest of the circuit and how much to go into the 2 ohm branch. And then again the same kind of thing will happen, because the rest of the circuit can be erased and instead of that rest of the circuit I can just put another 2 ohm resistor. So now at this place also the current has to split into 2 equal parts. So the current will break into 0.75 amps and 0.75 amps. It's as if the current knows beforehand what to expect in that entire circuit and behaves accordingly. And this is something very weird. We have still no clue how electrons do it really, but somehow they are able to do it. But electrons do a lot of other weird things, and compared to those weird things, this splitting up into 2 equal parts based on how much is the resistance later on in the circuit, that is nothing, you know. The next problem is again a very interesting problem, and the circuit goes like this. It might be given to you with some values, so you will have to keep in mind that with values it will become much easier, but I'm going to show you how to do it using variables, and using variables it might become long, so I will leave it at some point in between. But with values, this entire thing, you know, the entire sequence will go on. So let's say you have got a circuit where you have got a resistance R1, and then you have got R2, then you have got alpha R1, and then you have got alpha R2, and then you have got alpha square R1, and then you have got alpha square R2, right? And then you have got alpha cube R1, and then alpha cube R2, and so on. So the circuit goes on endlessly, right? And this is an infinite ladder, and there's one initial point A on the top left hand side and B at the bottom left hand side, and the job is to find the equivalent resistance between A and B. Find the equivalent resistance between A and B. Wow. So this circuit, now this is challenging enough, and what I want to do is I want you to actually first of all appreciate some kind of symmetry here. Let's say that I take 2 more points, C and D, after the first branch, right? And I just draw the circuit that goes beyond C and D. So I'm going to copy this and I'm going to paste it here, and what I've got is the circuit that goes beyond C and D, except I don't want the first one. So now let me say, if I had a circuit of this kind, and now if I have the original circuit with A and B, then what could be the relation between the equivalent that is across A and B and the equivalent that is across C and D? That's the question that I'm going to ask. And I see that A and B, okay, the upper circuit and the lower circuit are in fact exactly the same. They're exactly the same because I can redraw this circuit, the new circuit which I'm drawing, and I can say that alpha R1, let that be equal to R3. So I have got R3 here, and let alpha R2 be equal to R4. Then the next one will become alpha R3, and the next one will become alpha R4 here. The next one will become alpha R5, alpha square R3, alpha square R3, and the next one will become alpha square R4, and then you will have alpha cube R3, and so on, and the circuit will go on. So what I'm saying is that alpha R1 is R3 and alpha R2 is R4, and then I've got the same pattern which I had got for the top circuit. So the top circuit here had R1, R2 and alpha R1, alpha R2 and everything, and this guy CD has got R3, R4 and alpha R3, alpha R4 and so on. So if I find the equivalent of this entire circuit, let us say for the first circuit, the equivalent R between AB, so let me write that as RAB, let that be a function of R1 comma R2. It will be some function, it will be some kind of addition, multiplication, this, that, we don't know what it is, but then the resistance between A and B will be some kind of function of R1 and R2, and I'm going to represent that function as F, right? So F is that function. Now I ask you, what would be the equivalent resistance between C and D. Then so I should write a if somewhere here. So I will write if RAB is equal to f of R1 R2, then RCD is equal to, what will be RCD? So it will be the same format, the entire form of that expression will be the same, but wherever in that expression I had R1, I will have to insert R3, and wherever I had R4, I will have to insert R2. So sorry, R2, I will have to insert R4. So RCD will be a function of R3 and R4, and it will be having the same format, R3, R4. So wherever I had R1 in this equation, I will substitute R3. Wherever I had R2 in this equation, I will substitute R4. But then let's look at the relation between R3 and R4. So wherever I had R1, if I am substituting R3, it means I am substituting alpha R1, people. So I am saying that I am going to substitute alpha R1 and I am going to substitute alpha R2 in the same equation. So in the same equation which you had initially for the first circuit in terms of R1, R2, if you substitute alpha R1 and alpha R2 for every term, then from every term I will be able to take alpha common out, right? And I will get alpha times that function of R1, R2. Then what I will now say is, let me take this entire thing, copy it, that's the original circuit. So now I'm going to say that let R0 be the equivalent resistance between A and B, right? Then equivalent resistance between C and D becomes alpha R0. And then how will you be able to solve this problem? You just have to redraw the entire circuit and say that there is a point A on the left hand side on the top. So starting from there, the first one which I encounter is R1, then I encounter R2 in another branch that goes down, and then in place of everything else I will put alpha R0 because that's the equivalent between C and D. And now I can figure out the equivalent of these things. So I can find out the equivalent of alpha R0 and R2, and what will be that? So this entire thing will give me an equivalent of alpha R0 into R2 by alpha R0 plus R2. That's the answer that I will get from here, and this guy will be in series with R1. So therefore R equivalent between A and B is going to be R1 plus alpha R0 times R2 divided by alpha R0 plus R2, and all that is actually equal to R0. We have proved that using maths that it should be equal to R0, and if all the remaining circuit is alpha R0, then we should have R0 between A and B, and then if you solve this equation you will get the value of R0. That's how you get to the answer. And this is more challenging like this because you will get an expression containing R1 and R2, and I really don't have the enthusiasm to get that expression here, but you can easily get it. And if you have got values of R1 and R2, then it's a very simple equation to solve and you can get the value of R0. They will also have to give you the factor alpha by which all the resistances decrease. So they will say that often they say that it is R1 and then we have R1 by 2 and then we have R1 by 4 and then R1 by 8 or something. So you know that the factor alpha is 1 by 2. You will get all kinds of functions. You will get, say, I'm just assuming that maybe resistance between A and B is some kind of function of R1 and R2, right? So it will have some format, and there will be some terms in the numerator, and there will be some plus or minus between those terms in the numerator, and there will be some terms in the denominator, and there will be some kind of plus or minuses between those terms in the denominator. Right, with this I think there should be no issue. Now some people will argue that sometimes we have terms in multiplication in the numerator. So they will say, examples like we will have r, in some cases what we have is r1 r2 plus r2 r3 plus r1 r3 multiplied by some kind of r0 and by something, so we get equivalent expressions like this. All I'm saying is don't keep anything in multiplication. You multiply this r0 inside, so r0 r1 r2, r0 r2 r3, r0 r1 r3. So finally it is possible to get all the terms in the numerator with either plus or minus between them, and it is also feasible to get all the terms in the denominator with only plus or minus between them. And now here is the interesting part. One, I know that the total dimensions of this term should be equal to the dimensions of resistance. So if I have resistance to the power 4 in the numerator, I should have a resistance to the power 3 in the denominator, so that I still get a resistance in the numerator, because I want the dimensions to be alright. So I know that the degree, is it called the degree? Second degree, third degree equations, right? So the degree of all the expressions on the top in the numerator will be one more than the degree of all the expressions in the denominator. That's one. And second, I'm saying all, because whenever you have plus or minus signs between two terms, in physics the two terms must have the same dimensions. So if the first term here has got r power 4 kind of dimensions, the second term should also have some r power 4 kind of dimensions. Now it may not be r power 4, it may be r2 square into r1 into r3, some term of that kind. But then if you count the exponent of resistance kind of terms, you will get 2 plus 1 plus 1, so 4. Right, so if in every term in the numerator you have only got plus or minus signs in between, then each term should have the same kind of degree, and let's say each term has got fourth exponent here, and then we know that every term in the denominator should have got only third exponent. Fine. Now in the next case what I'm doing is I'm replacing every term with alpha times that value. And suppose there was r3 also, I would have done alpha r3 or something, So wherever r1 appears, I'm going to put alpha r1. Wherever r2 appears, I'm going to put alpha r2. So I will then get alpha to the power 4 in the numerator in every term, which I can take common, and alpha to the power 3 in every term in the denominator, which I can take common, and what will be left is just alpha in the numerator, and the remaining function will be the same as the function of r1 r2. Right, so that is why I am able to say that this will become alpha times function of r1 r2 r3 and so on.